This poster investigates how a PLA TiO3 glycerin composite and a TPMS geometry together control processability, mechanical response, and failure in FDM printed scaffolds. Additive manufacturing enables architected lattices with tunable properties, and triplet periodic minimal surfaces are a powerful design space for that purpose. Our goal was to fabricate printable composite filaments, print P-type Schwarz TPMS scaffolds, and relate composition and rheology to compression behavior and failure modes. The materials and printing workflow were chosen to be simple, reproducible, and compatible with low-cost hardware. We impregnated PLA 4060D with glycerin and incorporated BTiO3 powder to reach 85W% PLA, 10W% BT, and 5W% glycerin. The blend was hot mixed and extruded in a Brabender plastic order into 1.75 millimeters diameter filament, then sliced in Cura 5.6 and printed on a Creality Ender 3. The TPMS primitive cell was generated in SolidWorks from the Schwarz equation and tiled into a periodic scaffold that we used for compression tests. The composite structure and dispersion were validated by SEM EDS and XRD with Rietveld refinement. Cross-section SEM shows a rough PLA matrix containing BTO clusters, while global EDS maps of BA, TI, and O indicate an overall homogeneous distribution at the scaffold scale. The powder XRD pattern is well indexed to tetragonal BTiO3 with refined lattice parameters A equals B 3.99 more and C equals 4.026 mores, and a good fit quality Hihue 1.08, confirming phase identity post-extrusion. The rheology results explain why the filament prints reliably at modest temperatures. At 180 degrees Celsius, the pellet, neat PLA, and composite curves all exhibit pseudoplastic behavior, and the combination of glycerin and BT lowers the apparent viscosity relative to the extruded PLA baseline. This reduction widens the processing window, improves interlayer wetting, and allows stable deposition of thin TPMS struts without stringing. The filament-level mechanical response establishes the baseline for scaffold performance. Tensile stress strain curves show the composite retains viscoelastic characteristics comparable to PLA, with a moderate reduction in stiffness and strength that is typical for filled, plasticized systems. The retained ductility and compliant matrix are important to enable controlled, non-catastrophic collapse during lattice compression. The TPMS compression data reveal the key trade-off between stiffness and energy absorption. Compared with neat PLA scaffolds, PLA BTG lattices show lower initial modulus and peak stress, yet exhibit a broader stress plateau and higher absorbed energy before densification. The failure evolution shifts from brittle strut snapping in HPLA to progressive, elastoplastic buckling and layer-by-layer collapse in the composite, which is the desired behavior for scaffolds that must carry load while avoiding sudden failure. The failure micrographs connect composition to fracture mechanisms. In neat PLA, sharp shear bands and brittle ligament rupture dominate. In PLA BTG, crack paths are deflected at particle matrix interfaces, and plastic flow localizes around agglomerates, promoting stable collapse and distributing damage throughout the unit cells. The implications are that composition and architecture can be co-designed to target controlled failure in porous structures. For biomedical scaffolds, lightweight cores, or impact mitigation components, the PLA BTG TPMS delivers a practical balance: printability at low cost, tunable compliance, and enhanced energy absorption with predictable failure. The limitations suggest a clear optimization path for future work. Reducing BTO agglomeration via surface treatment or particle size control should increase strength without sacrificing toughness. Adjusting glycerin content will let us trade stiffness against printability, and systematic porosity geometry studies across TPMS families will generalize the structure property map. On the characterization side, statistical compression results, fatigue testing, and quantitative porosity metrics will strengthen the conclusions. In closing, the study shows that a simple PLA BT glycerin composite can be extruded into printable filament, formed into TPMS scaffolds, and engineered to fail in a controlled, energy-absorbing manner. This combination of accessible processing, validated structure, and purposeful failure behavior opens a path to application-ready architected polymers with multifunctional potential.